the 6th of March 1943. 8,000 feet above the industrial heart of Nazi Germany, Lieutenant Colonel Curtis E. LeMay's led B-17 Flying Fortress carved through a sky thick with flak. The Ruhr Valley sprawled below a landscape of smokestacks, railway junctions, and munitions factories that fed Hitler's war machine. Inside the cramped bombardier compartment, hunched over an apparatus that resembled a marriage between a telescope and a mechanical brain, Technical Sergeant James R. Murphy made microscopic adjustments to a device the Germans would later declare impossible, the Norden bombsight marked 15th. The instrument before him was a masterpiece of analog computing, 30 pounds of precision machined aluminum, bronze, and optical glass that could calculate bombing trajectories with an accuracy that defied the mathematics of aerial warfare. Its mechanisms contained over 2,000 individual parts, each manufactured to tolerances of 1/10,000th of an inch. The gyroscopes at its heart spun at 18,000 revolutions per minute, maintaining spatial reference with such stability that the entire device could sense the curvature of the Earth itself. In an era when most military technology was measured in tons of steel and explosive yield, the Norden represented something far more revolutionary, the weaponization of precision itself. German intelligence had acquired fragments of information about this device through captured air crews and crashed bombers. Their engineers, working in the underground laboratories of the Luftwaffe Technical Academy in Berlin-Gatow, had examined the reports with a mixture of skepticism and dismissal. Dr. Hermann Fottinger, one of the Reich's leading aeronautical engineers, had written in a classified memorandum dated November 1942. The claimed accuracy of the American optical bombsight, a circular error probable of less than 75 feet from 20,000 feet altitude, represents either gross propaganda or a fundamental misunderstanding of DSPs, ballistic physics. Such precision would require computational capabilities beyond any mechanical device constructed by human hands. Fottinger was wrong, and his miscalculation would cost the Third Reich its capacity to wage industrial warfare. The story of how America achieved this supposed impossibility begins not in the factories of Detroit or the drawing rooms of Washington, but in the mind of a Dutch immigrant engineer who understood that modern warfare would be won not through courage or ideology, but through the cold mathematics of trajectory and impact. September 1920. Rotterdam, Netherlands. Carl Lucas Norden stood at the docks, watching longshoremen load his belongings onto a steamer bound for New York. The Great War had ended 2 years prior, leaving Europe a graveyard of empires and a laboratory of military lessons. Norden, a graduate of the Federal Institute of Technology in Zurich, had spent the war years analyzing one particular problem: the catastrophic inaccuracy of aerial bombardment. During the war, Allied and German bombers had achieved hit rates that were, by any standard, abysmal. A study conducted by the British Royal Flying Corps showed that fewer than 5% of bombs dropped from 10,000 feet landed within 300 feet of their intended targets. Entire bomber squadrons would release their payloads over a general area, hoping that statistical probability and sheer volume would eventually strike something of military value. The strategic bombing campaigns of 1917 and 1918 had been exercises in aerial approximation, expensive, dangerous, and largely ineffective. Norden believed this represented not a limitation of aerial warfare itself, but a failure of engineering imagination. By 1921, working from a cramped workshop in Lower Manhattan, he had begun sketching designs for a device that would transform bombing from an act of aerial saturation into a surgical strike. His initial concepts drew from 3 disparate fields: naval artillery, fire control, astronomical telescopes, and the emerging science of analog computation. The fundamental challenge was deceptively simple to state but wickedly complex to solve. A bomber traveling at 200 miles per hour at an altitude of 20,000 feet needed to release its bombs at precisely the correct moment, not when the target appeared beneath the aircraft, but several seconds earlier, accounting for the bomb's forward velocity, wind drift, air resistance, target movement, and the Earth's rotation. The human brain, relying on visual estimation and intuition, could not perform these calculations with the necessary speed or accuracy. Norden's solution was to create a mechanical brain that could. By 1927, working with financial backing from the United States Navy, Norden had constructed the Mark III bombsight, a prototype that demonstrated proof of concept but remained crude and unreliable. The device used a stabilized optical sight, connected through a series of gears and cams, to an analog computer that continuously solved differential equations. The bombardier would identify the target through the sight, input data about altitude, airspeed, and wind conditions, and the device would track the target while calculating the release point. At the precise moment, the bombsight would automatically release the bombs. The early tests were promising but inconsistent. The mechanical components, manufactured with the tolerances available in 1,920 seconds machine shops, would drift out of calibration during the vibration and temperature changes of flight. The gyroscopes, which provided the stable reference necessary for accurate sighting, were prone to precession errors. The optical systems fogged at altitude. The entire apparatus was temperamental, requiring constant adjustment and maintenance. But Norden was persistent, and by the mid-1930 seconds, as the world slouched toward another global conflict, his persistence was about to intersect with America's growing realization that the next war would be fought from 30,000 feet. June 1937. Wright Field, Dayton, Ohio. Army Air Corps test pilot Captain Theodore H. Barth brought his Keystone B-6 bomber into a shallow dive toward the practice range below. In the bombardier position, Lieutenant William P. Fisher hunched over the latest iteration of Norden's device, the Mark 11th, which incorporated revolutionary improvements in gyroscopic stabilization and optical precision. The target was a white circle, 50 feet in diameter, painted on the desert floor. Fisher activated the sight, centering the crosshairs on the target as the bomber maintained its approach vector. The device hummed with the sound of its internal mechanisms, a complex symphony of rotating gyroscopes, meshing gears, and moving cams. Through the eyepiece, Fisher could see the target growing larger, the bombsight automatically adjusting its calculations as the range decreased. At precisely the right millisecond, determined by mechanical computation happening at a rate of hundreds of calculations per second, the bombsight sent an electrical signal to the bomb release mechanism. The 500-pound practice bomb fell away, following a ballistic path that combined forward velocity, gravitational acceleration, and atmospheric resistance into a single parabolic trajectory. 6 seconds later, it impacted 18 feet from the center of the target. The observers on the ground, including several skeptical ordnance officers who had questioned the program's substantial costs, stood in stunned silence. The margin of error represented an order of magnitude improvement over any previous bombing system. In subsequent drops that afternoon, the Norden-equipped bomber achieved an average circular error of just 62 feet from 20,000 feet altitude, a level of precision that transformed strategic bombing from a theoretical concept into a practical military capability. By 1940, with war engulfing Europe and the United States recognizing the inevitability of its own involvement, the Norden bombsight had evolved into the Mark 15, the definitive wartime version that would equip thousands of American bombers. The device now weighed 30 pounds and contained 2,032 individual components, including a complex gyroscope assembly that cost more to manufacture than an entire automobile. Each unit required 1,500 man-hours to build, and carried a unit cost of approximately $8,000, equivalent to roughly $160,000 in modern currency. The site was so highly classified that bombardiers were required to take a formal oath never to discuss its technical details, and the devices were equipped with thermite self-destruct charges to be activated if the aircraft was in danger of falling into enemy hands. The optical system employed a 50-power telescope with a field of view that allowed the bombardier to identify individual buildings from 5 miles altitude. The stabilization platform used 3 interlocked gyroscopes spinning in orthogonal planes, creating a reference frame that remained fixed relative to true Earth coordinates, regardless of the aircraft's pitch, roll, or yaw. The analog computer section accepted inputs for altitude, true airspeed, wind velocity, bomb ballistic coefficient, and target movement, then continuously solved the bombing equation, outputting steering commands to the autopilot and the precise release point to the bomb release mechanism. The integration with the aircraft's autopilot was perhaps the most innovative aspect. Once the bombardier activated the sight and locked onto the target, the Norden literally flew the airplane, making continuous micro-adjustments to the heading to maintain the precise approach vector. The pilot became, during the bombing run, a passenger in his own aircraft. This automatic flight control, primitive by modern standards, was nonetheless sophisticated enough to maintain the stability necessary for precision bombing even in moderate turbulence and under combat conditions. December 1942, Berlin, Reich Air Ministry. Reichsmarschall Hermann Göring slammed his fist on the conference table, sending reports scattering across the polished wood. Before him sat a collection of Luftwaffe intelligence officers and technical experts, their faces bearing the careful neutrality of men delivering unwelcome news. The reports detailed damage assessments from recent American daylight bombing raids over occupied Europe, raids that had struck railway marshalling yards, synthetic oil refineries, and ball-bearing factories with what appeared to be impossible accuracy. "You are telling me," Göring's voice dripped with contempt, "that the Americans are hitting individual buildings from 5 kilometers altitude, in daylight, through flak and fighter attacks? This is fantasy. This is the same American Air Force that couldn't organize a proper fighter squadron in 1918. They fly in straight lines like parade formations, and you expect me to believe they possess some magical device that violates the laws of ballistics?" Colonel Joseph Schmid, head of Luftwaffe Intelligence Section IC, chose his words carefully. "Herr Reichsmarschall, our photo reconnaissance confirms the damage patterns. The Americans are not conducting area bombing like the British night raids. They are striking specific industrial targets with a consistency that suggests advanced fire control equipment. But the German High Command, conditioned by years of propaganda about Aryan technological superiority and Anglo-American industrial incompetence, could not accept what the evidence presented. The notion that American engineers had developed a bomb sight superior to anything in the Luftwaffe's arsenal contradicted the foundational myths of Nazi ideology. German bombing technology, exemplified by the Luftwaffe 7 series of sights used on Luftwaffe bombers, was competent, but conventional optical sights assisted by mechanical calculators that required extensive manual input and provided accuracy measured in hundreds of meters, not tens of meters. The German dismissal of the Norden's capabilities would prove to be one of the war's critical intelligence failures. Rather than redirecting resources to develop countermeasures or equivalent technology, the Luftwaffe continued to attribute American bombing accuracy to either propaganda, exaggeration, or simply lucky hits. This fundamental misunderstanding of American technological capability would cascade through German strategic planning, leading to catastrophic miscalculations about the vulnerability of Reich industrial infrastructure. Meanwhile, 5 miles above Germany, the proof mounted with every mission. The 17th of August 1943. The sky over Regensburg, Bavaria. 363 B-17 flying fortresses from the 4th Bombardment Wing formed a steel river across the morning sky, their contrails painting white highways against the blue. Their target? The Messerschmitt Bf-109 fighter production complex, a sprawling network of assembly halls and machine shops responsible for 25% of Germany's single-engine fighter production. Captain Robert K. Morgan, bombardier in the lead aircraft of the 91st Bombardment Group, aligned his Norden sight on the distinctive H-shaped main assembly building from 29,000 feet. Through the eyepiece, magnified 50 times, he could see individual windows, the shadows cast by roof ventilators, the geometry of the factory complex rendered in sharp detail despite the 6-mile vertical distance. His hands worked the controls with practiced efficiency, adjusting for the 30-knot crosswind, inputting the updated altitude from the navigator, fine-tuning the stabilization. The flak was horrific. German 88mm and 105mm anti-aircraft batteries had ranged the formation, and black flowers of explosive death bloomed throughout the bomber stream. The air inside the aircraft smelled of hydraulic fluid, sweat, and the metallic tang of fear. The B-17 jolted and shuddered as shrapnel punched through aluminum skin. But Morgan's hands remained steady on the Norden's controls, the gyroscopes maintaining their perfect stability even as the airframe shook. The bombsight took control of the aircraft, making microsecond adjustments to the autopilot, walking the crosshairs toward the release point with mechanical inevitability. At the precisely calculated instant, 38 500-pound general-purpose bombs fell away from the lead aircraft and its squadron mates. 1.3 seconds later, the interval calculated to achieve optimal bomb distribution, the next squadron released. Then the next. Then the next. From 29,000 feet, the bombs seemed to fall in slow motion, tumbling end over end through air that grew progressively denser and warmer. But they were not falling randomly. Each bomb followed a ballistic path calculated by 2,000 mechanical components spinning and meshing inside the Norden sight. The calculations accounted for air density, terminal velocity, wind drift at multiple altitude layers, the Earth's rotation, and the forward velocity of the aircraft at release. 43 seconds after release, the first bombs impacted the Messerschmitt complex. The strike photographs taken by cameras synchronized with the bomb sight would later show a devastation pattern of almost surgical precision. The main assembly hall took direct hits that collapsed the roof structure and destroyed 27 nearly completed Bf-109G fighters. The machine shop complex suffered catastrophic damage to its precision tooling. The electrical substation that powered the entire facility was obliterated. Post-raid analysis would determine that 73% of the bombs released had landed within a 1,000-foot radius of the aim point, and an astonishing 41% within 500 feet. For comparison, British area bombing raids conducted at night against German cities achieved concentration rates of less than 20% within a 1,000-foot radius. The Norden had delivered not carpet bombing but rifle fire from 6 miles altitude. The Regensburg raid cost the 8th Air Force 24 B-17 seconds shot down and another 100 damaged, a grievous toll extracted by German fighters and flak. But the raid also cost Germany 3 months of Bf-109 production from a facility that could not be easily replaced. The strategic equation had fundamentally changed. Precision bombing was no longer theoretical, it was operational reality. April 1944. Schweinfurt, Germany. The city was a smoking ruin, its 3 main ball-bearing production facilities reduced to twisted metal and shattered concrete after repeated American precision bombing raids. Albert Speer, Reich, Minister of Armaments and War Production, stood in the wreckage of the Vereinigte Kugellager Fabriken plant, reading casualty reports by the light of still-burning fires. The numbers were catastrophic. German ball-bearing production had declined by 67%. Fighter aircraft, tank, and submarine production were experiencing severe delays due to bearing shortages. The Americans had not destroyed a city, they had amputated, a specific organ from the German war economy. This was precision strategic bombing achieving exactly the effect its theorists had predicted. By identifying and destroying specific bottleneck industries, ball bearings, synthetic oil production, aircraft engine manufacturing, the American 8th and 15th Air Forces were systematically dismantling Germany's capacity to sustain modern industrial warfare, and they were doing it with a level of accuracy that made each raid count, each bomb a strategic asset rather than a crude instrument of terror. The Norden bombsight enabled not just accurate bombing, but efficient bombing. In an era when every bomber, every crew, and every bomb represented precious resources that had been manufactured, trained, and transported across an ocean, efficiency was not merely an economic consideration, it was a strategic necessity. A single B-17 bombing mission consumed enormous resources: aviation fuel, bombs, ammunition, maintenance hours, crew training, fighter escort. The Norden ensured that these resources translated into meaningful strategic effects rather than random destruction. German industrial planners, belatedly recognizing the threat, began implementing desperate countermeasures. Critical production facilities were dispersed to underground sites, scattered across dozens of smaller plants, or relocated to regions beyond the range of American bombers. But dispersal carried its own costs: loss of efficiency, increased transportation requirements, vulnerability of supply chains. The mere existence of American precision bombing capability forced Germany to divert resources from offensive production to defensive reorganization. The psychological impact on German defenders was equally significant. Anti-aircraft gun crews and fighter pilots, watching American formations approach in broad daylight with apparent disregard for defensive fire, understood at some visceral level that they faced an enemy with technological capabilities that outmatched the Reich's industrial capacity. The Norden, though unseen by German eyes, became a ghost in the machine, an invisible opponent that seemed to guide American bombs with uncanny intelligence. By late 1944, the cumulative effects of precision strategic bombing had created cascading failures throughout the German war economy. Oil production, targeted with particular intensity by Norden-equipped bombers, fell by 82%. Aircraft production, despite Speer's heroic organizational efforts, could not compensate for the destruction of engine plants, aluminum production, and avionics facilities. The Wehrmacht's mechanized units, starved of fuel and spare parts, became increasingly immobile. The Luftwaffe, unable to replace combat losses or adequately train new pilots due to fuel shortages, ceded air superiority over the Reich itself. February 1945. Over Berlin. Second Lieutenant James R. Murphy, the same bombardier who had begun this narrative over the Ruhr Valley 2 years earlier, sat at his Norden site, tracking the Reichstag building through scattered clouds. He was 23 years old. He had flown 46 combat missions. His aircraft bore the scars of flak damage from dozens of raids. And he was, at that moment, preparing to destroy a building with sufficient precision that he could count the windows through his eyepiece. The moral complexity of his position was not lost on him. The Norden bombsight, celebrated in American propaganda as a tool of precision warfare, carried an implicit promise that American bombers would strike only military targets, that civilian casualties would be minimized, that the United States would wage war according to principles of discrimination and proportionality that separated American methods from the indiscriminate terror bombing practiced by both Germany and, increasingly, by British area raids. But precision is not the same as discrimination. A bomb that hits its target with mechanical perfection remains, fundamentally, an explosive device that kills through blast, fragmentation, and fire. German industrial targets were not isolated installations in empty deserts. They were factories embedded in cities, surrounded by workers' housing, situated near hospitals and schools. Precision bombing minimized but did not eliminate civilian casualties. And as the war ground toward its conclusion, As German resistance stiffened and American strategy prioritized unconditional surrender over negotiated peace, the line between military and civilian targets became increasingly blurred. The Norden enabled accurate bombing. It did not, could not, resolve the fundamental moral ambiguity of strategic bombing itself. American bombardiers, looking through sights that magnified targets to almost intimate clarity, could see the human geography of the cities they destroyed, the parks, the churches, the residential neighborhoods concentric around industrial districts. Unlike the RAF bomber crews who released their payloads through clouds, guided only by radar and pathfinder flares, American crews saw what they were destroying. The precision that the Norden provided came with an unavoidable burden of moral knowledge. Historical assessment of the strategic bombing campaign remains contentious. The United States Strategic Bombing Survey, conducted after the war, concluded that precision bombing had significantly accelerated German defeat, though at enormous cost, over 12,000 American aircraft lost over Europe, 43,000 aircrew killed, 87,000 tons of bombs expended. German civilian casualties from Allied strategic bombing totaled approximately 350,000 to 500,000, killed a horrific toll that raises enduring questions about proportionality and military necessity. The Norden bombsight did not make strategic bombing moral, it made it accurate. That accuracy served strategic purposes, disrupting German war production, forcing resource diversion, degrading military capability. But accuracy itself carries no ethical weight. A precisely delivered bomb that kills civilians is no more moral than an inaccurately delivered bomb that does the same, even if the former wastes fewer resources in the process. The 8th of May, 1945. Victory in Europe Day. The Third Reich, which had promised a 1,000-year dominion, collapsed after 12 years of existence. The Norden bombsight, which German engineers had dismissed as impossible, had helped write the obituary of Nazi Germany's industrial capacity. Over the course of the war, Norden-equipped American bombers had dropped 1.4 million tons of bombs on European targets with an average circular error that remained under 300 feet, a level of accuracy that would not be surpassed until the advent of laser-guided munitions 3 decades later. Carl Lucas Norden, the Dutch immigrant engineer who had conceived the device, lived until 1965, long enough to see his mechanical computer made obsolete by electronic systems and eventually by the satellite-guided weapons of the precision strike era. The Norden bombsight itself became a museum piece, a beautiful anachronism of gears and gyroscopes in an age of silicon and software. But the principle Norden had established, that precision is a force multiplier, that accuracy is a strategic asset, that technology can transform warfare from brutality into calculation, became foundational to modern military doctrine. The Germans had dismissed the Norden as impossible because they could not imagine that mechanical computation could achieve such precision, and because accepting American technological superiority contradicted their ideological assumptions. This failure of imagination cost them the war. Not alone, of course, the Wehrmacht was defeated by a constellation of factors, including Soviet numerical superiority, Allied industrial capacity, strategic overextension, and German leadership incompetence. But the Norden bombsight represented something the Third Reich could not counter. American innovation applied systematically to the problem of converting industrial capacity into military effectiveness. The bombsight that made the impossible routine, that transformed bombing from approximation to mathematics, that enabled a bombardier in a shaking aircraft surrounded by flak to place explosives on a target 6 miles below, with an accuracy measured in feet rather than miles. This device stands as testament to what engineering imagination can achieve, and as a reminder of the profound responsibility that comes with such capability. In the end, the Norden bombsight was neither salvation nor damnation. It was a tool, extraordinarily well designed, manufactured with obsessive precision, deployed with strategic insight, and operated by young men who faced death in the frozen sky above a burning continent. It could not make war clean or just, or anything other than the terrible human catastrophe that war has always been. But it could, and did, make war more precise. And in the calculus of industrial age conflict, precision proved to be the difference between victory and defeat. The device itself now rests in climate-controlled museum cases, its gyroscopes stilled, its optics dark, its mechanical brain silent. But its descendants, the GPS-guided weapons, the precision strike doctrine, the entire architecture of modern military technology, continue the work that Carl Norden began in a lower Manhattan workshop a century ago. The transformation of warfare into an engineering problem, solved through mathematics, implemented through technology, delivered with mechanical perfection. Human hands built it, human minds designed it, and human beings, in the terror and urgency of history's most devastating conflict, used it to reshape the world.